What we're going to talk about now is the application of the first law of thermodynamics to reactions. And maybe we should remember that the first law of thermodynamics says that any change in internal energy of a system is because it has either exchanged heat or work with the environment. That's what it's saying. So sometimes the heat is positive or, sorry, it's negative or positive depending on if it's lost or gained heat, and the same for work. Work can be positive if work has been done on the system, or negative if work has been done by the system. You will see that we have used this term of internal energy, so E, to express internal energy. For reasons that we will not have time to talk about. Sometimes this E will be called U or H. H is not exactly the same as internal energy, but in this course, at least GenChem1, we will say that it's the same. This H is referred as the enthalpy, and for all the practical purposes, it is a measure of internal energy, or in this case, delta H is a measure of change in internal energy, and we will use it mostly to study change of internal energy in reactions. So a typical reaction of combustion, right? You know that methane reacts with oxygen, it burns, right, to give carbon dioxide and water. If it gives out energy, you can imagine that again we are using that kind of graphical representation of potential energy. It goes from up to down. It means that if the y-axis is H, right, it's the enthalpy or internal energy, there is some energy loss now, not anymore in form of kinetic energy, because now this energy is lost to the system, so there's some heat out, therefore the total final internal energy is lower than the initial, therefore you're subtracting a larger number to the final. This is negative. We will call this an exothermic reaction, which makes sense. It gives off some thermal energy, in this case some heat. Okay. Notice that there are some reactions. This typical case of an exothermic reaction. Combustions typically are exothermic reactions. Other not chemical reactions, in this case it's a physical change, when ice, water solid, becomes water liquid. And this may be counterintuitive to think that it's an endothermic reaction. Please think about that. The internal energy of water liquid is higher than the internal energy of water solid, of ice. The molecules in water move faster, therefore they will have more internal energy. So one needs to provide some heat to warm up the molecules, to break some hydrogen bonds happening in ice that do not take place in water. Therefore, in a reaction like this, when you will have a positive increment of enthalpy or internal energy, we will call this endothermic. So we will use delta H to describe change of internal energy in a reaction. So yeah, of course, H depends on temperature, so this is something that we will definitely talk about that, because you will have different values of H, of enthalpy or internal energy at different temperatures. Let's solve a problem. In this case, there is a reaction of sulfur reacting with hydrogen to form hydrogen sulfide, and it gives you what we will call molar enthalpy. Notice that in this case, the energy is divided by the number of moles. And that's a very important part, because it means that depending on how the reaction is balanced, this value will be different. The way this is written, it says that the reaction will give off this much energy. Why will it give off? Because it's negative. Remember from the previous slide, it's negative, therefore it will give off energy for each mole of what? For each mole of any of the substances that has one in front. So in this case, for each mole of product. Okay? So let's answer these questions. Is this an exothermic or endothermic reaction? Well, we said that because this is negative, again, it means that delta H is final minus initial. To be negative, to be negative, it means that the initial internal the initial internal energy is larger than the final, this has to be therefore exothermic. Exothermic, okay? So another property of the molar enthalpy is that if you reverse the reaction, you just need to reverse the sign of the enthalpy. Okay, so in this case, you could imagine going from reactants to products. From reactants to products, the delta H was negative. Okay, because it's final minus initial. But when going from products to reactants, instead of final minus initial, you have initial minus final, and you will have the same number, but just changing the sign. So what is the delta H of the reaction for the reverse reaction? It's 20.2 kilojoules per mole, and this is positive. Okay, so let's do some factor conversion here, because it's asking for what is the change in enthalpy when you have 2.6 moles of sulfur reacting. S8 is a wonderful molecule. It's like 8, I don't know, 1, 2, 3, 4, 5, 6, 7, 8. It's a ring that sulfur forms, and it's in its most standard state. So if you have the opportunity to do a little bit of modeling, it's a very interesting molecule to look at. So again, so we are going to use 2.6 moles of reactants, and we're going to calculate how much delta H in the reaction that releases. So 2.6 moles of S8, let me erase this, S8. The reaction says, the way it's written, that 1 over 8 mole of S8 will release negative 20.2 kilojoules. So notice that we just need to do this factor conversion, which will be a negative, but we will be able to calculate how much delta H changes when we use these many moles. A trivial question, maybe, I hope. The question is in form of grams of reactants, of course 25 grams of S8. You have to calculate the molecular weight. You have the molecular weight of S8 is 1 mole, and then you attach the rest. 1/8 of mole of S8 will give negative 20.2 kilojoules. Again, this will be the answer.